First paper, the optimal choice of hypothesis is the weakest, not the shortest. Michael, welcome. Thank you.
All right, how's that? Is it still not sharing? Okay. Forgive me, it's a new computer, so all right. Give me a second. Yep. It has to quit and reopen. Fantastic. Oh no, it's system settings because of new computers. So, okay, now it's asking again, and I have to reopen Zoom. Okay, share screen. Yeah. Okay. This is called the optimal hypothesis is the weakest, not the shortest. It is about generalization and the ability to generalize. This is of interest for AGI because arguably intelligence is the ability to generalize because it's about the speed at which you can learn or the extent to which you can adapt given finite time and resources. So this is specifically about how to maximize the ability to generalize given certain assumptions. These assumptions are things like uniform distribution of tasks, finite number of, we're dealing with finite sets, environment with some regularity to it. So informally, to avoid getting stuck in the weeds, we assume that a parent is like a labeled data set, an ostensive definition of a task. And we've got child, which is a subset of that. And from child, we form a hypothesis. This is a program that could have generated child given certain inputs. And if that hypothesis also generates parent given an expanded set of inputs, we have generalized from child to parent by obtaining this hypothesis from child. So many processes could have generated child. We want the one that actually did, so we can generalize to parent. And this is akin to learning. So Occam's razor says the simplest is most likely to generalize. We usually measure simplicity by looking at the length of the program. So Kolmogorov complexity in the case of things like IXE or minimum description length. So this is useful for getting better accuracy when you've already sort of hit the point where you're interpolating data. Okay, so I propose an alternative to simplicity. It's called weakness. It's because of my first paper. I would have changed it, but it's stuck now. And so it amounts to given certain assumptions, and with some experiments and proofs, I show that maximizing weakness maximizes the ability to generalize, and that maximizing simplicity does not. A lot of assumptions involved in this. It uses a formalism of an active cognition, which basically means we end up with a finite number of possible states using declarative programs, it amounts to sort of inductive logic programming. And above all, it assumes a uniform distribution over tasks. All of this is contingent over that. So in terms of proofs, I prove it is necessary and sufficient to maximize the weakness of a hypothesis, to maximize the probability of generalization, and that it's neither necessary nor sufficient to minimize description length. And then probably of more interest are the experiments. So I compare weakness and simplicity. It's a very simple 8-bit string prediction problems with 4 bits input, 4 bits output. And the idea is to learn binary addition or binary multiplication. And generalization was considered to have occurred if and only if it sort of perfectly reconstructed the parent. The experiment setup, so generate 16 strings, 1 for each of the 4-bit inputs. Sample between 4 and 14 examples from this to see how the performance differed between minimum description length and weakness as I increase the number of examples. Then generate both a weak hypothesis and a minimum description length hypothesis, and then check whether they generalize and to what extent. This was done using things like A*. Record the result, repeat, trial many times, see what came out. So overall, the rate of generalization, so this is where it was sort of perfect. Both of them were able to do this, but weakness was between 10% better and 183% better for binary addition. And to the extent of generalization, weakness was between 7 and 56% better. And for multiplication, we saw a similar trend. So that covers the experimental results. And there are a couple of other things that follow from this formalism and some of these results. So they're mostly of philosophical interest, and they're going to be in my talks tomorrow on 2 papers dealing with the emergence of causal representations, arguably how you could construct an identity as an AI, the computation of meaning, sort of giving a mechanistic explanation of how we get the Gricean pragmatics given a formalism of AI, and theory of mind. So if you've got any questions, please come see my poster. It is the very small one. I'm going to pretend that was intentional as a joke about description length. All right. Thank you very much.
Thank you very much indeed, Michael. Sorry. And next up, we have got Harald Kjellin on the indications of suitable algorithms for an AGI. Thank you, Harald.
Yes, that's okay. Once I developed a system for the Swedish government, and then my personal experience from this was that it was entirely necessary for me to have this overview of the knowledge, because I was the main responsible, and if I didn't see exactly how it was reasoning, I couldn't detect where the errors were. So that made me probably very biased towards this. I believe that it's necessary to do, as many people here have argued today, to design AGIs similar to how a human being thinks. Not because that is better or more efficient or anything, but just because we need to be able to know how they represent their knowledge. We need to be able to check continuously. So I believe that we need to develop this relationship with the system. So after a while, we need to talk with the system and ask it to describe where they have problems, how they are, how mature they are on a higher level. So some of the discussions here today concern that AGIs are dangerous. They will control us. They will become like totalitarian dictators and so on. But if we look at human evolution, we see that the competition, the wars have in the end developed the democracy. When people are in danger, they have to cooperate. So democracies outcompete dictatorships. In a similar way, I think that it's naive to believe that any kind of restrictions on the AGI will work in the end. The Chinese military industry will not follow the directives from Europe and so on. So there will always be a lot of people. And it doesn't even matter if we try, because the genie is already out of the bottle. The spirit of this cannot be controlled. ChatGPT has many copies already out in the open source community. So the game is over. We shouldn't even discuss this. But what we can discuss is how can we engage in this power game with the intelligence that nobody controls? Well, I would say the opposite of what is going on would be very nice, to just open it up, to spread it out in the open source community, and then develop computers similar to how we think. And then we need to develop an emotional relationship with them. Can you imagine a parent that has a child, has to be very patient. The child is already all the time asking questions. Why is it like this? Why do you go to work? Why cannot I have money, and so on? This is how the child learns. And I think, isn't it quite naive to think that we will design very smart computers? And then we ask the question, how can we control them? They must, of course, develop their own purpose in a relationship with us. So we need to have an emotional relationship. In the beginning, it will be incredibly simple. We need a lot of patience. But then after a while, when this child, this AGI child, starts to do something that is reasonably intelligent, then we can start to ask, what do you want now? If we respect the complete freedom of these AGIs that develop everywhere, what will happen when the child is grown up? If a child grows up with a parent that says, you cannot do that, you cannot do that, you cannot do that, then you know what will happen with this child. It will become a very dangerous person, maybe a dictator. But if we treat a child with respect, this child will learn, not only from us, but from all the other AGIs, that it pays to cooperate. That's one of the basic rules of evolution. That is why we have democracies. So if we do this, we can expect this super intelligent AGI to be compassionate, caretaking, and this AGI would certainly not try to eradicate human beings. It would just try to support us. It would be smart enough to not be brutal. So I will not go into any details of the system designs I have. That would complicate it all. But this is 5 minutes. You got my message. Thank you.
Thank you for that bright, positive, and inspiring future, Harald. Right, Leonard is going to talk us through causal reasoning over probabilistic uncertainty.
All right. Thank you. All right, I hope everybody can hear me all right. So I'm going to be talking about, hi, first of all, my name is Leonard Eberding. I'm working with Chris Thoresen at the Reykjavik University on a reasoning system, which has many similarities to NARS, but works on a way more continuous state space and with direct sensor information. So what I'm concerned with is how can we get noise, for example, of sensors into the reasoning process of the system such that we can make predictions about the uncertainty of future states. I'm going to start with a with a little question. Why do we have to look at our own hands when we try to thread a needle? And how do we know that we have to look? And for me and my research, the answer to this is that we are able to reason with and about the precision of our own sensors, of our own actuators. So we know what we have to pay attention to just by knowing where we have erroneous data in our in and output stream. So how can we do this in a causal reasoning system? My approach here is to fuse the approaches from reasoning systems with approaches from probabilistic robotics, and thus extending deterministic causal models to include probabilistic uncertainty descriptions. So I'm trying to extend the reasoning mechanism to use uncertainty in its pattern matching and its reasoning process. What do we get from this? Multiple things. I think very important is a system that can adapt its own feedback loop frequency. So it knows when it has to do observations in order to achieve a goal. Additionally, a description of attention-worthy variables in the system's data streams. Better usability of sensor data without the need of pre-processing. And predictions not only about future states, but also about their uncertainty. Here's a very simplified example of what I mean. We have a system that is supposed to move through a restricted room, and it has some models about how it can move through this room. And here over here we have time t0, time t1, and time t2 in order to achieve this goal of being here. If we have uncertainty in our output streams, it might happen that the system tries to move to position T1, but ends up at some point before, then turning on the spot and crashing in the wall, or just moving too far in the first place. Another thing regarding the attention mechanism is this idea. If we can predict the uncertainty from a current state to a future state, and we have a goal that we want to reach, which is constrained in some way, we can predict whether our actuators will be precise enough in order to achieve the goal in its constriction. If it doesn't, we can do, or the system can do planned observations in between. So we can reduce the control magnitude, observe again, reduce our uncertainty of the state. And if we do that often enough, you're able to achieve the goal in its constraints. So planned observations can reduce the uncertainty enough so that the system can be sure that it will be able to reach the desired state space. And by doing that, we can identify variables that the system needs to pay attention to, others that, from your reasoning process, you realize, okay, those variables will be in line with what I want to do. I don't have to pay as close attention to those variables as I have to on those where I know I will have problems. I have a big poster outside, so please come and have a look if you're interested, regarding what this means for multiple causal chains that are in conflict with each other and similar. So yeah, that is my presentation. Thank you very much. And it's nice being here.
Thank you. Thank you very much indeed, Leonard Eberding. Right, George Wright is going to come and talk to us about self-comprehension for more coherent language generation. Welcome, George.
Oh, okay. Thank you. Yeah, thank you for having me. I'm George. I'm interested in language and perception and narrative, and maybe how narrative might be necessary for having a sense of self. But what I'm currently working in is quite a simple problem domain of temperature maps of an artificial island or a fake island. it kind of looks very simple, but you can see from some human examples that you can get quite a wide variety of interpretations and texts that humans will generate. So for example, some people will describe this as two parallel increase and decrease patterns on the map, whereas other people might describe this as a single warm area changing position and size. And then some other people might add further to their description with a preface, for example, in this case, describing it as a tale of two halves. So my thesis is that you need, in order to have a better and more coherent text, you need to not only to comprehend and recognize patterns in the original input, but also to do the same thing with the text that you've generated as well. So my architecture really focuses on recognition of sameness, differentness, and more and less relations in different conceptual dimensions. So for example, recognizing an increase involves recognizing two areas that are the same location, one at a later time with a higher temperature. And then the same sorts of relations can be used to match and recognize patterns between texts or between sentences to build a longer and more coherent text. For example, using conjunctions and pronouns if you recognize similar or the same word being repeated. So my architecture borrows from the copycat architecture, which performs analogies on simple strings. So for example, if you transformed ABC to ABD, how do you perform the same transformation to M, R, R, J, J, J? And it's based on using sort of relations across these strings. But basically, I've borrowed the copycat idea of having codelets and a code rack. So all the processing is broken apart across microagents called codelets. These will perform a small action like recognizing a chunk or labeling something or building a relation. And they also follow up with another codelet to do similar or related work with an urgency reflecting how likely it is to improve the quality of the structures. So each successive codelet is selected based on urgency. And this, there's a certain degree of randomness with selection. And this is determined by the satisfaction score, which kind of measures how good all of the structures and texts are that have been generated so far. So as satisfaction goes up, it becomes less random, and as satisfaction goes down, it becomes more random. So all of this kind of emerges from all of the interacting parts, and you get some texts out at the end. So here are some examples of that same map with the human examples. They're not quite as good as you can see here, but it also recognizes when it has done texts which are less good by having a lower satisfaction score. And then here are some examples where it does a bit better on an easier problem. And it kind of recognizes the difference between a good and a bad text. I think the reason why I think this is quite relevant to the idea of general intelligence is that you could use the same sort of process just as you recognize patterns on a map or patterns between texts. You could also recognize patterns in the program's own behavior to sort of watch its own behavior, and you could, to some extent, get some degree of self-awareness then. And this sort of thing was approached in something called MetaCat, which built on Copycat. Yeah, thank you, and see my poster.
Thank you so much, George. And on our home stretch, 3 more papers to go. A unified structured framework for AGI, bridging cognition and neuromorphic computing, Mingkun. Thank you.
Hi. Good afternoon, everyone. I'm Mingkun Su, and I'm PhD student in Tsinghua University. I'm very glad to be here to present our work. My topic is a unified framework for AGI bridging cognition and neuromorphic computing. And we are aware, cognitive architecture and neuromorphic computing are two promising pathways towards AGI. Neuromorphic computing mainly aims to replicate the functioning of neurons and encephalic regions by designing algorithms and compute chips, while cognitive architecture mainly focuses on building computational models of human cognition and mentality in higher level. Despite their different origins, they share the common goal of achieving AGI. Although they have achieved significant progress in their respective areas, both fields are often considered to be distinct and separate approaches, which may hinder the breakthrough for the AGI development. From the perspectives of development level, an AGI system can be viewed as three hierarchies, including the computation, algorithm, and implementation. And a matter of fact, cognitive architectures are at the level at the computation levels and are characterized by top-down design. It mainly focuses on modeling the high-level cognitive primitives and functionality modules and interaction rules. The dynamics, the information flows rely on the abstract functional connection and its constructed entities in a symbolic way. However, it neglects the underlying biological inductive bias. On the other side, neuromorphic computing is at the implementation level, while and characterized by the bottom-up design. It mainly focuses on modeling the biological details, but it lacks the top-down design from computation and cognition and cognition functionalities. So the two fields have developed separately in different levels. Obviously, there's a distinct gap between the two fields, and this is also our motivation to bridge the gap. In this work, we view the three hierarchies as in a graph structured perspective, and provide a modeling methodology of hierarchical neuromorphic graph. That is HNG. The HNG leverages the underlying dynamic spires to correspond to the high-level cognitive primitives via multi-stage dynamics process. For the framework mainly includes three levels. That is cognitive architecture, HNG, and the neuromorphic computing. The cognitive architecture can be regarded as a graph structure where the functionality modules and the interaction rules can be equivalent to vertices and edges, And at the neuromorphic level, the underlying spiking networks are presented as a graph structure form, and for arbitrary information form with various graph structures, the spiking network can complete computation of the information processing and representation of for the stimulus. And at the algorithm level, the HNG is a hierarchical neuromorphic graph. It can transform the high-level cognition process and the lower-level neuromorphic process into a unified multi-scale graph for computation and representation. The proposed HNG is a multi-scale graph. It can simulate the assembly dynamics and biological plausible graph abstraction. Obviously, it can be viewed several. It includes several sub hierarchies, and the information transforming process can also viewed as several hierarchies. From the top-down view, a cognitive cycle can be abstracted into several levels, including the function, control, representation, and computation. The function area can be designed to control the underlying neuromorphic brain areas based on the design rules with adaptivities. And the computation can be directly corresponds to the underlying computation units in neuromorphic level. And for the representation, from a bottom-up view, the neural level will first form convergent assemblies from via mutual projection after the dynamics, and then the assemblies will form the stable attractor structure, and then the attractor state will be connected following a prior in the transformed semantic space, and then this will correlated into the high-level cognitive variable. And for the information processing procedure, it is very simple. The information representation can be realized by our HNG and the assembly modules. And as for the computation, it can be realized by our inference modules. For the representation transformation, we use the attractor mechanism to finish the information transformation from the dynamics to structures. And for the inference and learning, each layer in our design network corresponds to a brain area, and the connection between two layers is actually the.
We need to wrap up. Let me hand you this microphone to wrap. Might need to be charged.
Thank you. The connection between two layers is actually the projecting passes between multiple brain areas. So the weight connection is dynamic during inference process, and the learning process is very flexible and compatible with multiple coding schemes and training strategies. We use the visual question answering task as the evaluation and implement our HNG as the intermediary sorry. Sorry. I'll be finished it. Okay, 1 minute. Sorry. The results, the experimental results reveal that the underlying neural dynamics can incorporate well with our designed hierarchical neuromorphic graph, and it also indicates that the robustness and homeostasis property of the of each brain area. And besides, it also indicates the weakness of traditional purely rule-based systems and the enhancement of our method on reasoning robustness. That's all for my report. Thank you very much.
Mayank Kejriwal. Are you here? Hi, Mayank. He's going to talk us through context-rich evaluation of machine common sets.
All right, testing. All right. So hi, I'm Mayank, and delighted to be here, and just wanted to briefly present our work on context-rich evaluation of machine common sense. So this is work done with my PhD student, Kjellin, and with colleagues from RPI, and the work is funded by DARPA. I want to just start by saying, hopefully uncontroversially, that building machines capable of common sense reasoning is certainly an important milestone, right? So necessary, but maybe not sufficient in achieving AGI. And if we think about what common sense is, right, it's sort of one of those things that we have, but it's very difficult to design. It's to define. But one sort of simple Wikipedia definition is it's sound practical judgment concerning everyday matters. So the word everyday really important, and a basic ability to perceive, understand, and judge that is shared by nearly all people. So how can we know that a machine has common sense, right? And so as with so many problems in AI, let's do an evaluation. And in fact, there have been many evaluations in natural language processing and computer vision to evaluate machine common sense, especially in the last, I would say, 5 years. So here on the right, you see an example of from 5 data sets, actually. So let's just see the first one, which is abductive natural language inference. So basically, you're given a prompt, right? So that's the portion in yellow. So these are, let's say, 2 observations. Jim was working on a project. Luckily, he found it on a nearby shelf. And what you have to do is select a hypothesis that is most likely to be true. So that's why it's abductive rather than deductive. And in this case, Jim found he was missing an item is most likely the hypothesis that is connecting the 2 observations. So we need to get machines to do this, and then they are evaluated on accuracy, right? So this is what we call multiple choice question answering. And such data sets can be manually created, automatically generated, crowdsourced. They've been done in all kinds of ways. They test different aspects of common sense, such as social intelligence, physical intelligence, ANLI, and so on, right? So far, it's so good. But unfortunately, this kind of evaluation has limitations. So first of all, right, if we think about our common sense, we don't go around, answering multiple choice questions. There is so much more than that to human common sense. And even if we ask such questions, current benchmarks treat each question as an IID instance. So, there's no, it's sort of like it's like taking a standardized test. You answer a question, you move on to the next question, to the next question. So it's kind of these small mini tasks rather than sort of more comprehensive task with dependencies and planning and so on. And there's a real sense in the community that many of the benchmarks have been gamed due to continuous testing. So even before ChatGPT and all these big language models, some of the earlier generation of language models like Unicorn were already coming very close to human performance on physical IQA. And I think we can sort of agree that we are very far away from true physical intelligence in even state-of-the-art AI. So from some of the leaderboards, that's what you would believe, but it's not true. So something is wrong with this kind of evaluation. It has merits, but it should not be the only thing to evaluate machine common sense. So what we are suggesting and proposing is this context-rich method for evaluating machine common sense. And as you can see here, this is sort of a more sort of iterative, open loop session. That's what we call it. So in this one, it's almost like you're conducting an interrogation with the machine, but with the goal of evaluating common sense. So let's say that you start by testing the comprehension abilities of a machine. So you give it a context, you ask a question, you ask it to give you an answer. But then, right, you can ask a follow-up question, testing counterfactual reasoning, and you can ask a follow-up question. And so we have actually done this kind of evaluation with ChatGPT and with some of the other language models. And it turns out that this is a richer way of evaluating machine common sense. And this method, in fact, shows that, although the big language models are getting closer, they still make mistakes that you would not expect from an entity that has common sense. So if you're interested, come talk to me more, and I'll be happy to show you our ChatGPT logs and walk through some of the findings that we have encountered. So, yeah.
Thank you very much. And that was really interesting. Hao Zheng, tell me how I'm pronouncing that. Hao Zheng is here to talk us through coherence in intelligent systems. Thank you.
Is that okay? Well, thank you so much for bringing me here, and it feels fantastic to this big family, I think. And the topic that I wanted to share with you today is the neural coherence for general intelligence. And can anyone have a guess about what I'm going to talk about? I think most topic here is very hard to predict what the people are going to talk about. So I will show you in the next following minutes. So the basic motivation is that, in my personal opinion, as far as I know, that all living systems, as large as human beings and as small as a single cell or virus, could surprise us now and then with their mysterious behavior that I think is intelligent. So, and the generality of their intelligent behavior is still far beyond most current artificial systems. So I wonder what is the gap between the two types of systems. And perhaps one of the basic fundamental difference between the artificial and living system is that the artificial system usually use the equilibrium state to represent things like the object, features, concepts, symbols, or relations, like the static feature map in a feed-forward neural network. The living system, on the other hand, prefer to use non-equilibrium states to, to operate or to like operate in non-equilibrium states that is indicated by various type of rhythmic behaviors and the transient synchronies. And now here, the neural coherence generally refer to those spatial temporal states that a large amount of computing units that is correlated together so that the synchrony and rhythm emerges. So it seems to me that coherent state is indeed a very important state for some essential mental operations like consciousness or awareness. And in the temporal spatial theory of consciousness, Nosov proposed that the nestedness of temporal and spatial structure of the neural activity could account for the level of the consciousness. So it seems that coherence is indeed an important concept. So my question is, how can we conceptually link neural coherence to the general intelligence? And on the other hand, can we build up neural coherence to solve computational problems that is related to AGI? So that is the basic thing that I wanted to discuss. And the key picture and the main point are summarized in this page. From a point of view of searching in a dynamical and distributed system. So there are two general assumptions, very general, maybe too general. And the first one is the AGI needs to search for solutions of various levels, one after another, for its goal, for its survival. So it needs to search. The second one is that the system itself should have a way to know when the solution has been found. In other words, the solution should be indicated. Based on the two assumptions, I will show that what is the dynamical nature of the neural coherence and why it is important for AGI and how to build up neural coherence based on principles. To be more specific, at representational level, I think neural coherence is a temporal aspect of the solution itself that is represented as cycles. And at functional level, I will show that neural coherence could serve as indicators of the solution. And what is special is that coherence could act as universal and internal indicator in a distributed system. And at implementational level, I show that the neural coherence can build up from principles, and the principle is called the self-evidencing. And at implementation level, I show two demos on two general computational problems that is related to the emergence of perceptual awareness. The first one is the binding problem, a very old problem in psychology, neuroscience, and neurosymbolic literature. And this problem cares about how distributed informations like different features like color, shape, texture, voice, you name it, those distributed information could combine and be grouped or bound together to form a whole entity or whole object. For example, a percept of a person that we recognize. And the temporal binding theory guesses that the binding information could be expressed as neural coherence, like here. And the second problem is the part-whole hierarchy problem, a very challenging problem for distributed system, which asks how to dynamically form a parsing tree of a scene or of a concept in a neural network. So a tree in a neural network. And my guess is that the nested structure of the part-whole hierarchy could be accounted for as a nested temporal spatial structure of neural coherence as here. And that is my demos. And to sum up, in both cases, the solution is searched in distributed system and is represented as coherent state. And that is the sketch of the model. And the basic principle behind is very simple. In a word, it is neural coherence could be built up from self-evidencing between two things. One of them is the top-down attention, maybe by a word model. And the other is the bottom-up called incidence filtering or coherence filtering. And here is a snapshot of the results on the grouping problem or the binding problem. Well, given the ambiguous input, the system needs to search for solutions so that different objects could be segregated. And starting from random state or random guess, the searching gradually converges to the coherent state, indicated by the coherence measure. And in this state, the binding solution is represented as the neural coherence. And along the way, the gamma-like oscillation emerges. So this process is inspired or similar to what is happening in the neural cortex. And for more details about the model, the result, or the idea behind, welcome to my poster and discuss. So thank you very much, that's all.
Thank you so much, sir. How? All right, folks, this was absolutely thrilling. Thank you for these very highly talented, skilled researchers for all these papers. We're going to just do a very short Q&A because we've got posters outside, we've got some demos. So I'm going to take one question from YouTube, one from the audience. And there's one that's been waiting on YouTube since this morning from Yasantha, is asking Mohammed Reza Ali Doost, who's still with us today, this afternoon. And Yasantha asks, thank you, Yasantha, for your questions, asks, is the VEI values of narrow AI versus AGI? And can VEI consider as a valuation aspect of AGI? Mohammed Reza, I hope you understand that. And
Hello
already.
again. Yeah.
Hello again.
Hello again. Thank you for your question. I have to mention that, let me share my screen shortly. I had to omit this portion, this section, because of the time limitation. Versatility and efficiency, which I designed VEI based on this, are two necessary conditions for AGI. An AGI agent has to be versatile and efficient. And what does it mean? Based on the two definitions from Leckhatter and Penetrin-Gertzel, versatility means a wide range of easy to complex environments, and efficiency means perform well. And when we talk about AI, we are talking just about efficiency and not versatility. And when we talk about AGI or NGI, like what is happening in humans, they can also perform well in a wide range of easy to complex environments. So they would have a higher amount of VI, and they can perform in a wide range of environments. But AI just perform well, but in a specific and narrow range of environments. So the VI for AI is low, and the VI for AGI and NGI are high. Thank you very much.
Thank you very much, Mohammed Reza. Thank you for your paper. Right, any questions here in the room? And also, I think all of our speakers are going to be out with posters anyway, so you get a chance to go speak with them individually. Anyone in the room? I'm going to closed.